Then he moved to Institute of Plasma Research, IPR, Gandhinagar for his postdoctoral research work. After that, he went to Ben Gurion University of the Negev, Israel, with the BCSC, that is Blostein Center for Scientific Cooperation postdoctoral scholarship. Here I should mention that his excellent research work in plasma physics was highlighted in the popular science journal Physics Today, a reputed international science magazine journal. So without going any further, we'll start our main session in short. But before that, I would request our honorable principal, Sitananda College, Dr. Shamu Mahali, to say a few words. Sir, are you there? Principal sir, are you there? Am I audible to other? Ravindra Babu, can you hear me?
Hi sir.
Principal sir আছেন? হিমাংশু স্যার, আপনি যদি একবার প্রিন্সিপাল স্যারকে একটু কল করেন। রবীন্দ্রবাবু,
হ্যাঁ স্যার,
আপনি একবার ফোন হিমাংশু বাবুকে একবার ফোন করবেন স্যারকে, যদি একটু ইনভাইট।
হ্যাঁ ওকে।
Dr. Shaw, can you just share your slide, the first page? Maybe other people can see the title page. Principal sir had joined, just joined. হ্যাঁ স্যার, আপনি যদি একটু, আমরা যা শুরু করব আমাদের ওয়েবিনার, আপনি যদি কিছু বলেন আমাদের উদ্দেশ্যে।
আচ্ছা। হ্যালো।
হ্যাঁ স্যার, শুনতে পাচ্ছি। হ্যাঁ স্যার, হ্যাঁ শুনতে পাচ্ছি।
হ্যালো হিমাংশু, হ্যালো।
হ্যাঁ স্যার,
শুনতে পাচ্ছ তোমরা?
হ্যালো,
শুনতে পাচ্ছ?
হ্যাঁ শুনতে পাচ্ছি স্যার।
আচ্ছা, ওকে। ন্যাশনাল সেমিনার or state level? Which level seminar we have? State level or?
State level seminar, yes. Yes sir.
State level seminar organized by Department of Physics, Sitananda College Nandigram, with collaboration with IQAC on the topic National Dynamic and its application to complex system. Our distinguished resource person, speaker, Dr. Pankaj Kumar Sahu, Assistant Professor, Department of Physics, Rajapriyo Mohan College, Uttarpara, will deliver lecture on national nonlinear dynamics and its application to complex system. I hope that with the help of his lecture, all the professors, audience, students, scholars, and other person will enrich on the topic nonlinear dynamics and its application to complex system. What is nonlinear dynamics? Simply, in a sentence, I want to discuss here that in mathematics or physics or in any science, a nonlinear system is a system in which the change of the output is not proportional to the change of the input. So anyway, on the topic, our resource person is there, and my colleague, Professor Himangshu Hajra, Joint Coordinator, and Coordinator Shomo Jana, and IQAC Coordinator Dr. L.K. Dolai, and others audience and my other colleagues are present here in this COVID situation. Himangshu Hajra, Professor Himangshu Hajra, and Professor Shomo Jana has organized this webinar. So I give them thanks from my chair, many thanks, and my resource person, who is also agreed to deliver lecture on that topic, is also a person of thanks. I don't prolong and don't elaborate my lecture. I will ask to my colleagues that start the seminar, and I wish seminar will success and all will benefit it. Thank you.
Thank you so much, sir.
Okay, Himangshu,
Okay.
continue the program. Okay, Somo and Himangshu, continue
Thank
the
you,
lecture.
sir. Thank you, sir.
This person is present or not?
Yeah,
Is
yeah,
present?
yes, sir. Yes, sir. This is
Then you
Dr. Shaw is present here.
Okay.
Okay. Thank you, sir. So now I move to the main session of today's webinar, and I invite Dr. Shaw to deliver his lecture now. Dr. Shaw.
Am I audible?
Yes.
The PPT is visible. So,
Yeah, it's visible. Yeah.
okay. Thank you. So, first I would like to thank Dr. Soman for such a nice and kind introduction. And I would like to thank the organizing committee of this webinar from the Sitananda College to invite me here in this webinar to deliver a talk. So today I'm going to talk about the nonlinear. As I was informed that the most of the audience will be from the undergraduate student background. So the level of this talk will be of somewhat the basic, so that everybody can understand and appreciate, and so that they can take some message and carry out their study in the field of research. So the whole presentation was prepared like that. So I will start with what is nonlinear dynamics. As we know, recently the nonlinear dynamics has been introduced in the undergraduate curriculum in the many West Bengal universities. So some of the students have already went through it. Some will be go in the future. So the important is what is nonlinear dynamics, and then we will see some important and universal dynamics of nonlinear system. Why I am calling it universal dynamics? Because you all know that nonlinear system is an interdisciplinary research subject. It may be from the physics background, from the chemistry, from the biology, finance, social, traffic, anywhere. Almost all the real world systems are nonlinear. But the important fact is the underlying dynamics, whether their physics is different or chemistry is different, is other aspect. But when we talk about the dynamics, the nonlinear dynamics, the principle behind them is always same. So that's what the important fact about it. That's why we're calling it universal. Then we will see what the complex system is. And as I am from the physics background, so for an example, I will show you the two complex systems, plasma and electronics. Mostly I choose electronics so that the student can perform some tabletop experiment in their college itself on the nonlinear dynamics so that they can appreciate their studies. We will see the application, why the nonlinear dynamics is helping in such a kind of subject. Is not only the mathematical tool to study, but it also helps to understand many complicated physics or chemistry behind the dynamics. And then I will finally give you some ideas about tabletop experiment so that you can perform in your college by yourself without help of any faculties to study the nonlinear dynamics, and even if you are clever enough to generate some novel work from out of that. Okay, so we start with the nonlinear dynamics. So first we need to know what is nonlinear system. The system in which change of output is not proportional to change in input. How we can understand it? We start with some textbook example, Duffing oscillator. Suppose I gave you a Duffing oscillator, a black box, you don't know what is within it, and you want to check whether the system is nonlinear or not. So what you have to do? You have to give some input. Let's say input is f cos omega t, or some kind of forcing, and there is an output which is your oscillation from this oscillator. Let's say it's x, and suppose the value of f is 0.5, and in the output you are seeing this kind of periodic oscillation, very nice periodic oscillation with the amplitude approximately 0.45. Very good. Now we slightly change your input, that is increase your forcing strength from 0.5 to 1.0. And certainly you will see the oscillation is still same. However, amplitude is increased, and that's what the intuitive you can easily guess. When you have increased the forcing strength, the amplitude of oscillation should increase, and that's what exactly happening, and that's what happened in a linear system. Now your amplitude of the oscillation, output oscillation,
Pankaj, we can't hear you. Eh, uh, Pankaj, can you hear me? Ravindra, can you hear me?
Yes, sir.
I think there is some connection problem with the speaker. Okay, let me just. So, dear friends, please wait for some minute. Be patient. I think there is some connection problem with the speaker. I am just coming back. The speaker lost the connection. He's just coming back. Okay, I just informed him. So please stay there. So
Hello, I'm
Pankaj joined.
audible now.
Yeah, you are
Yeah,
audible.
yeah. I'm really sorry. Some fluctuation in broadband connection, and automatically I came out, and I was not in the window, so I was unable to check whether I'm audible or not. I was just speaking. Okay.
Yeah. It is okay. Just carry on. Yeah.
Okay. So
So maybe I think we lost you near the where you are discussing about the equations that uh, oscillatory equation there. I guess. Yeah. From here. Yes.
so this slide was completed or not? Means I was not aware of it.
Yeah.
Okay.
That sounds. Yeah. This slide. I think you are at this page. Yeah.
Okay. So let me restart again. I'm really sorry for that. So, non-linear system I was discussing when the change in output is not proportional to change in input. And to understand that, we took an example of dumping oscillator. And suppose I gave you a black box, a dumping oscillator, and you don't know whether this system is linear or non-linear, and you want to check. What you have to do, you have to just give an input. Let's say it's a force omega t, and then you need to take output, which is x, and you started collecting your data. So when force was 0.5, what you have seen oscillatory equation, oscillatory behavior, which is very nice, of the amplitude 0.45. And then you have increased your forcing strength to 1. And what you have seen that forcing strength increased, as a result, your output amplitude is also increased to 0.9. And that's what the linear system is. We can easily guess that with the increase of forcing strength, output will increase. Okay. Now, when I say the forcing stress is 3 times, then you can easily guess that your output should be 3 times larger. But interestingly, output is no longer following the input. Now what we have, a chaotic oscillation. And that's how we can confirm that even black box is a nonlinear system. I don't know what kind of system it is, but only I know I have given input, I have taken out output, but it's no longer a proportional. And that's why we can say the given system is a nonlinear system. And whether it's a physical or chemical or biological, I don't bother. I have a black box, and when I want to explain this kind of behavior, I can simply write a dynamical equation for it, okay, which is given by this equation. Okay, so now you can easily see that this is the oscillator. It's contained the op-amp, resistor, capacitor, but I'm not bothering what kind of system it has. I can simply write the dynamics with with one mathematical equation, and that's the beauty. Whether black box is a physical or chemical or biological system, I don't bother. I can simply write an equation, and I can explain everything. So that's how nonlinear dynamics help us to understand very complicated system which contain many components, and we don't able to integrate them in an easy way. But nonlinear dynamics provides us a very easy, elegant way to explain that system. And almost all real-world systems are nonlinear, and often their dynamics are chaotic, unpredictable, and counterintuitive. Yet their behavior is not random. In the example, we have seen that final output was a chaotic, so we can say that this is random. But actually, they are very deterministic because we can generate them from a given equation. So once we know the equation, the system is completely deterministic. Okay. So behavior of any nonlinear system can be described in the form of mathematical equation, and as a result, we can explain that system. So overall, nonlinear dynamics is a branch of science which study the dynamics exhibited by the nonlinear system. So what is nonlinear system and how we can see that given system is nonlinear dynamics, now we know about it. So we move to another point, universal characteristic of nonlinear system. As we know that nonlinear system is interdisciplinary research subject. I am talking more about it, that it can from the physics or chemistry or biology, but we can explain them with the help of one equation without bothering what is the composition or component of that system. So once we can explain with an example, that means underlying dynamical feature must be same. That is, the rule will be the same. So whatever kind of nonlinear dynamics you will get in the system, you can easily explain with the help of nonlinear dynamics. Okay, and for example, bifurcation. Bifurcation is certain qualitative change in dynamics. That's what we seen in the example. Initially, the oscillation was periodic, and suddenly it's become chaotic. Okay, so that's what we call the bifurcation. So there are many types of bifurcation: saddle node, transcritical, pitchfork, period doubling. For an example, let's show you the period doubling. This is the phase-space plot of a periodic oscillation. That is one period. You can assume like a sine oscillation. So if you plot the phase-space for that, you will get one circle. And with the change in parameter, when you have a two period, so you will get two loops in the phase space. That's what we are getting here in the plot B. If you increase further, it becomes a four period. That's why we are getting four loops. And finally, we have a many period, that is system become chaotic. Okay. So from a deterministic system, we can easily get the chaotic thing. And this thing happens in all the systems. So I got in the plasma physics, I got in the electronics, somebody has got in the chemistry, biology. But what is the important is, here we are getting bifurcation, which is in the nature of period doubling. That is, root from order to chaos is period doubling. Similar phenomena is chaos, which is shown in the plot E. This is random, unprecedented, and sensitive to initial condition. What do you mean by sensitive to initial condition? Suppose somebody started from x equals to 0, and at time t, he is at x equals to something, let's say x1. And at the same time, somebody else is started from x equals to 0.00001. Then he will land up some different position, which is completely different from the initial one. So if two persons started from very nearby but not exactly same, they will end up their final position in the very far location. So that's why chaos is very sensitive to initial condition, and as a result of it, chaos has very important result in application. It's look like a random, but it has a very important application, like data encryption, where secretly somebody wants to send the data from one location to other location. They use the help of chaos, because you can incorporate your data in the form of chaos and send to your receiver and give them initial condition, exact initial condition, then he will be able to locate the final. But if somebody don't know the initial condition, then he cannot predict. He will not find out the exact location. So that's what the importance of chaos is. There are other phenomena, synchronization, resonance, fractal, all sorts of nonlinear phenomena there. It's universal. So now we will start its application. Why nonlinear dynamics is so important? So we see its application in the complex system. So complex systems are composed of large number of non-linearly interacting components whose aggregate activity is non-linear and not derivable from the summation of the activity of individual components. So for an example, suppose your system have 5 components, and if you take the dynamics of individual 5 components, and if you take the dynamics of complete system performance, then if you add those 5, you will not get the original one, because they are interacting among themselves. So aggregate activity is non-linear, and you cannot find them by adding up the individual components. Example are fluid, condensed matter system, biological system like neurology. In neurons, we have millions of neurons in our brain. They are interacting with each other. Social system, humans are interacting among themselves. Traffic, cars, plasma, financial system, everywhere we find the complex system. But the fourth point is very important. Despite of their wide diversity, universal law and phenomena are similar. Means they can have same kind of nonlinear phenomena, and their universal laws are same. So if you understand the complex system, if you explain some behavior in the field of fluid, you can easily extend your idea to traffic, and you can explain the traffic data as well. So it helps you to switch between one field to another field. As a result, you will never have shortage of research problem. I started with the plasma physics, then I did work in the electronics, and then I moved to Israel and I was working in the field of ecology. So the major component is nonlinear dynamics, and their dynamics are same, so I was able to use my expertise. So that was the very interesting fact about this. So that's why I like this subject very much. So because of all these properties, this emerged as a new scientific discipline, okay, and recognize the interdisciplinary research subject. So I start with the 2 examples. The first one is the plasma, and then electronics for the students. So what is plasma? So if you heat up a solid, it will become a liquid. When you heat up a liquid, it becomes a gas. If you heat up a gas, it becomes a plasma. So plasma is nothing but ions, electrons, and neutrons. So here the burner are just for the representation. You don't think that you have to heat up gas on the burner. Heating up means providing energy. So there are lots of ways to provide energy in the gaseous medium, and when they have a sufficient energy to overcome the molecular forces, then they will break apart, and it will form you ions and electrons. Okay, and then finally you will have a plasma state. Plasma is very common, like solar plasma, your tube light in your household, which is not exactly plasma, but they consist of ion, neutron, electron, and neutrons, but they are not qualified for the plasma. but you can have a rough idea from that. So, due to abundant nature of plasma, this is recognized as the fourth state of matter. And we have seen it consists of large number of ions, electrons, and neutrons. So this must be a complex system because ions have their own dynamics, electrons have their own dynamics. At the same time, they are interacting with themselves. So it is a complex system. And as being a complex system, it must exhibit complex and nonlinear dynamics like multi-scale dynamics, chaos, intermittency, mixed mode, oscillation, and etc. Now, first question comes in my mind or somebody else's mind that what to do with the nonlinear dynamics in plasma? There are a lot of physics to explain everything. Then why we need the nonlinear dynamics? It is a mathematical tool. So there are some challenges in plasma study where nonlinear dynamics comes help. The first important and major goal of plasma to produce clean energy source, okay, with the help of fusion. Like on the sun, we got the energy from the sun, but in the sun, all the energy is produced using the fusion because once you dissociated your hydrogen atom into ions and electrons, then two hydrogen ions fuse to produce a helium ion, and at the same time they produce lot of energy. So fusion is a very clean source of energy, and it produces very high energy efficiently. So the major goal of plasma study to make that is to create a mini sun on the Earth. I'm not going into detail of plasma. So, but the major challenge is to fuse those hydrogen ions. You need to have very high temperature, and you need to keep your plasma in some kind of container. So if you put your plasma in some kind of container and temperature is very high, then there is no material available on the Earth which can sustain that high temperature. They will simply melt down. Scientists came with the magnetic confinement of plasma. They put a magnetic field so that plasma can be confined around the magnetic field. But due to various instability in the plasma, which is a kind of nonlinear dynamics, there is very difficulty in the confinement. So we need to get rid of this instability. In order to get rid of something, you need to understand that. And in that understanding, nonlinear dynamics becomes very important. Similarly, apart from that major goal, there are very important minor goals like industry application, in film deposition using plasma. There, the challenges is depending upon plasma behavior, the surface structural property of thin film can be different. So there, if you know whether the plasma is chaotic or not regular, then you can correlate that studies. So what we have seen so far in the plasma, chaos, somewhere helpful, but somewhere it's very difficult. Means I don't want chaos sometimes. And to do that, chaos control is one of the important area in the plasma physics. So how we can control the chaos? Either you have to change the physical things, which I don't want, because I want the application of plasma. So how we can play with the plasma? So I need to control externally. So I need to understand the dynamics so that I can create some kind of feedback network or whatever to control the chaos. So here, this is the role of plasma. So let's see some result and application. So this is the simple setup because you cannot go and directly work on the tokamak for this kind of nonlinear study. So you always need some kind of tabletop experiment. So we started with the glow discharge plasma, and this is a very healthy device used in many industrial applications. This is the picture, and right hand side we have the schematic diagram of it. So it consists of a vacuum chamber, which is evacuated to a base pressure, and then we filled with argon gas. And here in the right hand side, you can see a cylindrical cathode of length 17 centimeter and diameter 10 centimeter, and this black one wired anode as a 3 millimeter diameter. And we supplied the voltage across this anode and cathode so that gas inside that system can be dissociated into the plasma. So that's how we have created the plasma. And to capture its dynamics, we put a Langmuir probe, and you can understand Langmuir probe as just a simple metal, just a simple metallic tip which is placed inside the plasma. As it's a metal, electron and ions can hit on that, and depending upon their fluctuation, you can easily record the fluctuation of plasma in the oscilloscope. So it's a very simple, just name it the Langmuir probe, but it's physically is just a metal tip which is made of copper or any other metal. Okay. And to do our study, we have placed a magnet, bar magnet, simple bar magnet, which is available in your laboratory. And we have changed the distance of bar magnet from the cathode so that we can change the magnetic field inside this cathode chamber. Okay. And these are the simple plasma properties at that experiment: plasma density, temperature. Okay. So directly come to the result. What we have seen when we have changed the magnetic field strength, this kind of oscillation. And the remarkable thing about this oscillation, you have always seen this kind of oscillation in your textbook. It's the periodic, still periodic, C is also periodic, D is also periodic, and then suddenly C, E, and F, they are chaotic. So here my system is going from the order to chaos system. And so far, I don't have any idea about the physics. Only thing I know that I have changed the magnetic field and I have gone from order to chaos. And to verify them, I just plotted the phase space plot, and what we have seen that one loop, then two loop, then four loop, and it has become a chaos. So it is period doubling route to chaos because one period is going to two period, to four period is going to four period. So period is getting double, 4 to 8, 8 to 16, and then chaos. So here we have period doubling bifurcation. So our nonlinear dynamics knowledge gave us one input that whatever you have observed is a bifurcation, which is period doubling route to chaos. Now here one important thing, that as we are changing the magnetic field by changing the distance of bar magnet, it is very difficult to change minutely. So a small variation is very difficult to manage. So we will not able to locate exact bifurcation point when system changes from 2 period to 4 period. But we are sure that system changes from 2 period to 4 period. But exact location is unknown to us. And this is the one plot bifurcation diagram. You can easily see these dots are representing the period. So initially 1 period, then 2 period, 4 period, 8 period, and it finally went to chaos. So now what should be the motive of any experiment? To explain that, to know the reason. So first we get the idea from the nonlinear, it's a period doubling bifurcation. Let's bring some physics into it and then finally fuse both to get the final result or explanation. Before doing that, this is largest Lyapunov exponent plot. Even if you look, some signals look like chaotic, but they may be periodic of higher period. So you cannot count that there is 30 period or 32 period. So we usually say it's a chaotic, but in real, they are periodic. So to confirm that, largest Lyapunov exponent is one of the calculation to confirm whether signal is periodic or chaotic. For a periodic signal, it should be 0. For a limit cycle, it should be less than 0. And for the chaotic, it should be greater than 0. So here what we found that for a periodic, it is almost around the 0. Why it's around? Why it is not exactly 0? Because it is experimental signal. Experimental signal always have some noise. And that noise may deviate your signal something from periodic to little bit. That's why it is around 0, not exactly 0. But we have seen that certain jump. That means system is changing from periodic to chaotic behavior. Okay? Now bring some physics. So as we are changing magnetic field, then system is changing. So what's the role of magnetic field here? So look at this point, this picture. We have cathode surface, which is negative potential. And if you place magnet here, then we have magnetic field lines, which is looking like this. Now just assume that some electron appeared at position A, then they will gyrate around these magnetic field lines. There will be a cyclotron frequency associated with it. Then what will happen? Due to that, that electron will follow this magnetic field line trajectory and it will come back at position B. But as soon as it comes to position B, it will encounter a negative potential and it will bounce back and again move to point A. So there will be a bouncing motion between A and B, and electron will be trapped there. And as a result, the ionization in that region will increase. There is another thing, because this is bar magnet, so field strength are different at different locations. As a result, the cyclotron frequency will be different at different locations, and in your system, you will have large number of frequency. As a result, they will interact among themselves and to produce what we call the internal noise, which is not very high to change your data, but nonlinear dynamics is very sensitive to initial conditions. So this internal noise can change your dynamics. Even though they are very small, they have a significant role in the dynamics. And as I said that there will be increase in ionization. To prove this theory, just look at this picture. When magnetic field was 0, there was no glow. With the increase of magnetic field strength, which is more prominent around 9 Gauss and 16 Gauss, you can easily see in this picture there is a bright region around the cathode surface where we have placed the magnet. Okay, and which is encircled boxed by a red dot, so it will be easy to denote that. Okay, and due to this glow, we have a localized glow region, and as this glow region have more ionization, so plasma property in this region can be different from the bulk of plasma. So we have two plasma regions, and this may interact to produce this kind of oscillation. And because there are more ionization, so there are more electrons, as a result there will be a local potential minimum. Okay? So what I am proposing from my physics knowledge and whatever I have seen as an observation, that this region interact to produce a period doubling bifurcation, and from the nonlinear domain I got that we have a period doubling bifurcation. Now I am proposing this theory, and you may argue that whatever you said, it's wrong. So I need to prove it, and to prove that, here comes the major part, the application of knowledge. Whatever I said the physics, let's make the model out of it. Because finally, nonlinear dynamics we can explain with the help of one equation. So let's make a model out of it. So I said that I have a potential structure with a minima. So I just wrote my potential structure like that. You find this potential structure in many plasma papers. So there is no question on that, which looks like this graph. So now my oscillation is due to ion dynamics. Just write an equation. Just to have idea of Newton's law, just write. Right hand side is the acceleration. So in left hand side, we must have left hand side we have the acceleration of ion. So in right hand side, we must have acceleration. So first term is due to electric field, which is generated by this potential. We have a dissipative term, which is due to the collision of ion. And then third one is very important, because I am proposing that the glow region is interacting. So I need to put that glow region as a forcing, because I am measuring my dynamics in the bulk plasma, and I am saying that glow region is forcing my bulk plasma region. So I put a forcing term. So simply with my simple knowledge, I have written this term with whatever physics I proposed. And if my theory is right, then it must produce same result. If my theory is wrong, then this must not respond to exact result. So to solve any equation, you have to normalize it. So we have normalized this some plasma frequency, some characteristic length, and this is the final equation. Here A, B, B, F are given, and mu is known to us. Omega P is any plasma frequency using which you can normalize it. So almost A, B, B, F, these are known to us. Okay, and some are not known, so we can approximate that value. And here force F is a control. So in practical, we have increased the magnetic field strength. So here you can also increase the forcing strength and look at the result, the period doubling by 4. 1 period, 2 period, 4 period, 8 period, and then chaos. So it's not a quantitatively matching, but qualitatively. So whatever theory I have proposed is true. That's what the model is proving. And even though this result is very simple, this is the bifurcation diagram of that. So even though its result is look like a copybook result, but it's very remarkable that in plasma physics, such a complex system we have able to found it. And we have shown the role of magnetic field, which is very important because bar magnet is using everywhere nowadays in many plasma applications. So that's why this paper was very important and highlighted by the physics student. Now, you may question that why you chose the plasma system. Because plasma system has wide variety of nonlinear dynamics. It's not only so the period doubling bifurcation, depending upon the pressure which you are giving and discharge voltage, you can show different dynamics. So on a single system, you can do whatever the nonlinear dynamics you can think of. The second one is spiking and bursting, which is another nonlinear dynamic. It is a multi-scale because it has a rest period and then the spiking period. And why I'm showing this, because for the first application, fusion, we have seen that plasma transport, which is one of the phenomena, which take the plasma from the core to the edge of the container. As a result, they are producing difficulty in the confinement of the plasma. And this spiking and bursting data have shown that kind of behavior. Once you know the correlation behavior of this kind of data, you can easily try to minimize them. Okay? So I'm not discussing much of details of plasma here. I'm just focusing on the dynamics part. So this is the plasma fluctuation. And you can easily see initially there are few bursts, spike and rest period. Then bursts are increasing. And with the increasing burst, system is settling to the spiking state. So this is transition from bursting to spiking. Okay. Now plasma don't know anything about the nonlinear dynamics. But if you look at their data, it's saying that system is changing from rest period to spiking period. If you plot the phase space, it looks like a closed loop, which we call the limit cycle. So system is losing its stability from rest period to the limit cycle oscillation with the help of fold bifurcation, which is some kind of saddle node bifurcation. So see, physics don't know, but dynamics is a bifurcation. And if you look the neurology data, and if you look the neurology paper where you find the bursting from the spiking, you will get exactly the same kind of result. And if I don't tell you that I got this data from neurology or plasma, then you will not able to dissociate what kind of data it is. If I don't show you the axis and the data's amplitude, then you will not able to say whether this data is came from the physics, plasma physics or neurology. And that's why this nonlinear dynamics is so important. I know the plasma physics, I know the behavior of the spiking and bursting, and suddenly you gave me the data from the neurology, neurons, and I will look at their data, I will try to find out what kind of dynamics it is, and I will be able to explain that. And then finally, you need a little bit of knowledge to correlate with the final result, because at the you cannot cycle lose its stability to the rest period with the help of again fold limit cycle bifurcation. Now, let's say what's the physics behind it. physics behind it, that we have seen in our experimental setup, there are large area difference between anode and cathode. Okay, so due to which, as electrons are moving towards the cathode, the electron collecting surface is very small. As a result, there are a crowd of electrons near the anode. You can think of that just like a puja pandal. We have a very narrow opening, narrow gate, but there are a huge crowd. And then suddenly, when you reach around the gate, you will find out there are a lot of gathering around the gate. But far away, it's very vacant. So that's what exactly happened. Electron, when they reach the anode surface, there are a large gathering of electrons because cathode surface are very huge. They are producing large number of electrons, but the collecting area is very small. So there are electron gathering. As a result, there are one different kind of potential structure form, which we call the double layer. And this double layer continuously forming and disrupting. So once they are forming, they are stable. We are in the rest period, and suddenly they disrupt. There are physics behind it. Why they are disrupting? I'm not explaining that. When they disrupt, they release lot of ions. They will directly move toward the cathode. As a result, there is a spike in our data. And
Pankaj, can I ask one question here?
Yes.
A double layer means, are you talking about a double kind of double well potential kind of thing?
No. A double layer is not a kind of double layer potential. Double layer in the plasma sense, whenever you have a large potential difference in very small area. Like if you look at the potential curve in whole plasma, so from the cathode, let's suppose I'm just don't bother about the signs and the numbers. Let's suppose you have a plasma potential of 10 volt throughout your bulk plasma, and suddenly when you reach your anode surface, there are huge number of electrons. So what will happen? Due to this electron, your potential will drop, and suddenly you drop from 10 volt within a range of millimeter from 10 volt to 1 volt.
Okay.
And then there will be a rise in the potential because you have to match that potential of your anode surface which you are giving from the outside. So there are huge difference in the potential. So it's look like right hand side is something different and left hand side is something different. So there is a double.
Okay, I see.
So double layer of plasma. So this is the double layer. Okay. And due to that, there is instability form because there is a huge potential difference. So there are more ionization, and suddenly when the ionization is beyond the critical one, that double layer disrupts because they are not able to handle that pressure. They are accumulating, they are creating more ions, and then once ions are strong, they are repelling all the electrons, and then they are producing one spike. So that's how we are seeing the spiking and bursting, and I can confirm that result by just measuring the relaxation time of that spike. So this is the physics behind it. Now, as I said that plasma don't know the nonlinear dynamics, but look at this curve. What we have seen in the data looks like a random. Bursts are appearing randomly here and there. But if you plot the interburst interval, just measure the interval between two bursts and take an average and plot with respect to discharge voltage, what you will see that best fitting curve look like this, which have power law behavior. That is, interburst distance is proportional to inverse of discharge voltage. And exponent is -1. That confirms here that system is changing from bursting to spiking behavior via intermittency route to chaos. Because this law is valid for intermittency route to chaos. So again, there is an inbuilt universal dynamics, intermittent route to chaos. And this is also reported in neurology, intermittency route to chaos. So, if you don't know what the black box is, if I just cover my plasma setup with some black cloth and I will say, take it this output, this is my input, do whatever you want, then you can easily explain all this data with the help of your knowledge of nonlinear dynamics. And suddenly somebody came and changed that setup to something else, still you will be able to explain. So significance I have already discussed the lecture continuation that permanent magnet This is very important application in plasma processing because they use the dipolar magnetic field. So if you know the application of the dipolar magnetic field or the role of dipolar magnetic field, then you can easily correlate or improve your result. And as I said, if you don't know the root cause of any instability, how you can get rid of it? You don't know the illness, then how you can cure it? So once you have to know the root cause, you need to know the instability, then you can easily cure. Okay. Then you can use this result in space plasma also because our Earth is kind of giant magnet. So if you know the effect of magnet on the plasma, how plasma trap, you can extend those two. Okay. So what is the future scope? So I have said many things, but can you do anything in that? So this is the future scope. Ideally, people represent plasma, characterize the plasma in terms of density, temperature. But can you characterize your setup? Suppose you have a setup, you want to work on that for a year. You can easily characterize the setup in terms of nonlinear dynamics that at particular discharge voltage, the dynamics was periodic. At particular discharge voltage, dynamic was chaotic. At particular discharge voltage, dynamic was spiking. Once you have your chart with you, then you just apply, do whatever application you want to do. And if you came to know, okay, in case of chaos, this application is giving this result. In case of spiking, the result is giving something else. Then can you easily characterize. And then suddenly you change your setup and you know that, okay, at this temperature, at this discharge voltage, it is spiking. Then you can easily say, okay, my result will be this. So there is a scope. You can characterize your data. You can correlate plasma fluctuation with the surface of thin film which you want to create. It's another important work which is also going on in IIT Kanpur. People are working on that. Put the bar magnet inside a plasma chamber and study the plasma confinement using dipolar magnetic field, which is a very highly, what I say, interesting area, and very few work is there, so you can do. And then you can develop a numerical model for different plasma features, and you can just direct link between plasma and numerical. So now let's move to electronics, because whatever I said in the plasma, there are very few people in the audience who can access those devices, because most of you are the students, so in your lab you don't have, and you don't have access lab of many universities or research institutes, so you may not get. So what you can do, you have studied and you want to explore right now, just like a summer project. So we can start with a simple electronic experiment. And I'm starting with a Duffing oscillator, which you have read in your textbook. And the idea of this experiment came from the summer student. We used to hire a summer student, and this topic was given to one of summer students whom I was helping. And from the tabletop experiment, we were able to generate one novel result. So there has been a growing interest in recent years in the particular class of oscillation we call the antiperiodic oscillation. What is antiperiodic? Antiperiodic oscillation is obey this relation: xt plus capital T is equals to minus of xt, where T is the time period of antiperiodicity. Means after the antiperiodicity time period, there will be a phase change in your data. So you can understand from a very simple example, sine oscillation is an antiperiodic oscillation. Okay. If the periodicity of sine is 2 pi, then antiperiodicity time will be pi. But all periodic signals are not antiperiodic. That's the catch. Because sometimes with the name, people think all the periodic signal will be antiperiodic. No, this is not true. All antiperiodic signal can be periodic. It is periodic, not can be, it's periodic. But not all periodic signals are antiperiodic. So, one of the important things you need a non-linearity. So you must have a nonlinear oscillator or nonlinear any kind of system. Here we started with the force dumping with a negative stiffness. So this is the equation we started with. We have chose all these parameters and kept K as a variable parameter. And what is the output result is this oscillation. Depending upon different parameters, you can get the period doubling and other things. But as we are interested in antiperiodic oscillation, which is a kind of new oscillation, Here you can see picture A, we have 3 peaks, but if you look this picture carefully, the hump are in the periodic state and the below minima are in the antiperiodic. Means if you just check exact symmetric diagram, okay, 2 humps are 2t apart and 1 hump and 1 minima is t apart. So with the increase of forcing strength, system is changing from the 3 peaks to 5 peaks to 7 peaks. But important thing is they are antiperiodic oscillation. And there are very interesting nonlinear dynamics behind it, which you can explain with the help of fixed point stability analysis. When you will read in your book, you will be more comfortable with these terms. But you can explain this 100%. But what my motive is to encourage students to do this kind of experiment in their lab, their own. So this I have first solved using RK4 method. This is the bifurcation diagram. You can easily see in this region 3 peaks, then 5 peaks, then 7 peaks. And you can just look from the 0, it's the other way around, symmetric kind of thing. So here number of peaks are increasing. So what we said is period adding cascade. Means period are adding on top of that 3, then 5, then 2 added 7, then 2 added 9, then 2 added 11. It's going on. So this is called period adding cascade. Okay. Now, as we want to perform experiment, just create an experimental analog circuit diagram for it. And to create it, you don't need help of anybody. You already studied in your SEM 2 or SEM 4, depending upon your universities. Look at this. First one is adder circuit. You have already performed. Here I have used LF356 op-amp. You can simply use 741, whatever available with you. Then integrator circuit. You know that. Integrator circuit, amplifier circuit, inverting amplifier. You just need multiplier, which is already available in the market. You just ask in your lab. It's hardly available in 30-50 rupees. Depending upon circuit you need it, you may not need it. Just combine them. I will show you how we can make this circuit. Then you can easily construct such a complicated equation in the form of analog circuit. And this is the experimental result. See, it's antiperiodic oscillation, 3 peaks, 5 peaks, 7, 9, 11, 13. You may ask why it's not 15, because my forcing, whatever is there, and my sign forcing, the strength amplitude of that amplifier was not enough. It was maximum up to 6 volt, 6. So I went up to 6. After that, if it is available, it will get the 15 and all the 0. So this is experimental result, and this is corresponding the test space plot. So it's look like for 3 periods, 3 loops, 1 bigger, 2 smaller. For 5 period, 5 loops, 1 bigger, 2 smaller, and 2 1 is further smaller. Okay. So this is experimental. However, there are certain difference that qualitatively is matching, quantitatively is not matching, because you have to scale up or scale down. And one thing I forgot to mention, all the resistance or capacitor is chosen in that circuit such that I can map those with my coefficient of that equation, x double dot plus delta x dot. So I can match those delta alpha beta. Okay. Now, as it is not scale up or scale down, in order to match exactly, we can easily confirm whether my numerical and experimental result are from the same law. And if you plot the number of peak versus forcing strength in the logarithmic scale, whatever you see, a simple power law. And look, left hand side for the numerical, right hand side for the experimental, and we have a perfect fit, a state law where the force, where the power is 0.34. There is a change in third digit. As I said, that experimental result always have some kind of noise in it, so you cannot match it 100%. But after point, it's match up to 2 digits, which is very remarkable. So we have same power law for the numerical as well as experimental result. So what we were able to convey this message, we have succeeded, and finally it's a kind of noble result. So we were able to publish also. What is significance? So we have explored the non-dimensional APO in the non-dimensional system, low dimensional system. Before that, very few paper available on APO, and there people saw the APO in very complicated. Suppose you want to use the application, you want to do application of APO, and you want to give APO into some signal or generate, or you want to give APO as an input in some device. So either you have two options: either make a complicated system, which other people have showed you, or make very simple dumping oscillator, which you know from your college days. Whatever will be easy for you, either construct a complicated or just the simple one. And for study purpose, it's also very important. You can generate the regular, irregular kind of pattern from the dumping. So if you want to demonstrate some student, you can use this. You can demonstrate chaos, you can demonstrate the periodic, you can demonstrate the limit cycle, all these things, just to tune that resistance and capacitor, and you are done. So this circuit is very robust and easy, and you can explore all kind of dynamics, and you can train your young student. Now, I'm done. Let's start with some idea of tabletop experiment. I request a student to just try. There are no harm in the try. You can try in your home also. Instead of power supply, you use battery. Okay, just purchase a 3-volt, 9-volt battery. It's easily available in the market. Just purchase. If you want to purchase op-amp, you can do it. It's hardly you need 500 rupees to set up that experiment in your home itself. So suppose this is an integrated circuit, and for time being, just assume that input is x double dot, and output must be minus of x dot. And depending upon RC, there will be a coefficient. I'm not going into that. You can calculate it, or you can choose RC such that coefficient will be 1. And due to inverting connection, it will be minus of x dot. If you put that output into another integrating circuit, output will be x. If you put that x into any inverting circuit, it will become minus x. Okay. Now we have input x double dot, we have output minus x. If you connect input to output according to Kirchhoff's voltage law, now we have output connection and input connection at same potential. That means our x double dot must be equals to minus x. Otherwise, it can't be true. So we can write equation x double dot equals to minus x. And what is it? This is the simple harmonic oscillator equation. So see, using 3 op-amp, you just created a simple harmonic oscillator. And you can just check your oscillation. Similarly, if you want to create a different kind of oscillator, just use the combination of inverting, non-inverting, multiplier, or adder circuit. If you want to add something, if you want to add x double dot with x with minus x, just use adder circuit, take the input from all 3 terminal and fit it there. So you can create the circuit. So you just take any equation from your textbook, just give a try. And you never know, you always get some kind of novel result out of it, because in my research life, whatever I've seen, that out of 3 summer students, always 1 student get the novel result. And when I was in SIP, with help of my faculty, we used to train at least 10 summer students in a year, and out of 10, 3, 4 usually gets the novel result within a month or 2. But sometimes they have to pursue, because they leave after 2 months, they come back, and then finally they did it. If you want to study more, then there are called magnetic pendulum. You can find in the Google. Just put 3 magnets, 1 pendulum, which is also a magnet or iron ball. Just give a push. It will start oscillating with different kinds of pattern depending upon initial condition. Okay. So if you want to improvise in this result, you can put 4 magnet, 5 magnet, take a picture, take a video, analyze those data. You can get a novel result out of it, if possible. Then there are other tabletop experiments for the chemistry student. BZ reaction, just type in the Google, bromine with acid. If you put that, you will see the color is oscillating. Okay, so if you leave that reaction for the long time, and if you record, you will see that the color of your that chemical solution is oscillating from one color to other color in a periodic fashion, depending upon some other agent. It may be chaotic fashion, and there is very important research going on in the BZ reaction for the pattern formation in BZ reaction. Very important result. And there are other experiments tabletop. You can easily search. So with this idea, hope all this talk makes sense to all of you, and it's sure motivate some of the students. Even if one student gets motivated, I will be succeeded. Okay, so thank you all of you for such a patience and careful listening.
Thank you, Pankaj, for such an excellent talk. Now we are open to take questions from the audience. So, audience, you can directly ask your question to the speaker, or even you can put it in the message. Please go ahead. So, in the meantime, we are getting questions from the audience. So, can I ask some questions to Pankaj?
Yeah. Yes. Sure.
Yeah. So, the first thing is that so you in your talk you talked about that saddle points. These are the basic things, but I want to just refresh because there are many students are there. So, saddle points are in the are those in the phase space diagram? Are those at the unstable points or?
No, the idea behind the saddle point is there is certain change in your characteristic of fixed point. Suppose you have a stable fixed point. Stable fixed point you can correlate with the potential minima. Okay, so you have a stable fixed point. Like if system is want to be in rest, it wants to be in the rest. Okay, and you are changing your parameter, what we call the bifurcation parameter, and suddenly you see that rest period loses its stability. Means now, suppose you are stable at x equals to 0, and with the change in parameter, suddenly that x equals to 0 become unstable. Okay. So, and with that, there is other creation of two more. So one become unstable. Whatever you are in the stable phase, x equals to 0 was stable. Now it's become unstable, but as a result of which two more other branches form, which may be stable or may be unstable. So now with one branch you have three branches. One is stable and two are unstable, or one are unstable, two are unstable, depending upon the kind of bifurcation you are talking about. Or there is another thing. Suddenly, suppose x equals to 0, you don't have any fixed point, and you are tuning your bifurcation parameter, and suddenly one fixed point form. So this is also a second sudden fixed point, because there was everything was unstable, and suddenly you have a stable fixed point. So came out of blue. So this is the stable saddle bifurcation.
Okay, and that. So when this bifurcation diagram means the at what situation the system becomes chaotic from this period doubling situation or bifurcating situation to when goes into the chaotic system, means I think the bifurcating when the there is period doubling is occurring, that situation is it can we call it totally chaotic situation, or chaotic situation is I mean, it depends on the parameter, bifurcation parameter, or that
Yeah.
particular system parameter.
See.
That at particular point it becomes
Yeah.
completely. It cannot completely recognize, or it cannot correlate between
Yeah.
the two positions.
Okay. I got your point. So actually, this bifurcation, when system become chaos, is totally depend upon bifurcation parameter. But there is a law. When the system is going from the 1 period to 2 period, 2 period to 4 period, there is a constant called Feigenbaum constant. So if you know when system transiting from 1 period to 2 period, and you know that constant, then you can exactly pinpoint when your system becomes 4 period, when your system becomes 16 period.
Yeah.
So as long as you can count 16 period, 32 period, you can easily confirm, okay, I am in the periodic domain. But it cannot last for longer. Means after 32, you cannot count 64. You may not have, because your system becomes so sensitive that it's no longer 64 you are able to count. They become a chaotic, completely unpredictable. So it's totally depend upon the bifurcation parameter, your other parameter. But however, once you started in that bifurcation domain, 1 period to 2 period, then it is governed by a law. From there, Feigenbaum constant is derived. So it has to follow that.
Okay.
Similarly, in other bifurcation pattern, again, there's intermittency route to chaos. You have a period, and then you have a signal which is completely intermittent. You don't know whether to characterize, just like in spiking case, the bursts were appearing randomly here and there. So those kind of intermittent, you don't know where it will appear. If you say recording your data, it will appearing somewhere, and finally it's become a chaos. So there are different routes, but in the 98% case, you will always have a period doubling route to chaos, and there are other route to chaos that very rarely observed. Okay, only in the 2%.
I see. Here, Soban Sundar Dhuria have a question. He is asking what sir said about that bromine and acid reaction, how that color changes.
Okay, so I'm not expert in the chemistry, but when I was started studying the nonlinear dynamics, so I got this example in my mind because one of faculty members told me. So when you put acid in bromide, so obviously there will be some chemical reaction. I don't know what kind of that. So, but due to change in concentration of plus minus whatever the content is there, they have their chemical property, and because of that reaction, their chemical property changes, and as a result, their color changes. Because whenever the chemical property will change, color will also change. So at one point, the concentration of one component increasing, as a result, color is changing from, I think, the pinkish to greenish color kind of changes happen there. So when one concentration is increasing, they will be pinkish, and then again, because of their concentration is high, they start backward reaction, and then their concentration drop, and other component concentration increase, and they become green. So chemistry people can explain better way. Maybe I'm wrong, but this is what happening.
Okay, I hope that answer to the question of the
But it's easily available in the Wikipedia.
Yeah. It is just standard chemistry question. Okay, another question is from his. What is the role of the magnet suspended? So also I. So I am. Maybe.
Tabletop.
Yeah, maybe he's talking about tabletop.
Actually, in this case. This is called the magnetic pendulum. It is also available. Okay, so you have 3 magnets here, and suppose you are giving a magnet here. So this magnet and this magnet, suppose they are in the opposite polarity. So when you just displace this and you bring this magnet on the top of this magnet, so there will be attraction, and this pendulum will not oscillate because they are in the fixed point. Somebody has catch him.
Yeah.
Okay? So there will be a fixed point.
Right,
and suppose they are in the opposite polarity. So when you put the magnet on top of this magnet, they will repel. So it will repel, and it will goes to some other direction. When he reaches somewhere, when this magnet reaches somewhere, it will get a repelled from other direction, then other direction, so they will start oscillating. Okay, the pendulum will start oscillating. So depending upon the polarity of magnet, there will be attraction, there will be a repulsion, and that interacting force that magnetic ball or iron ball. You can put the iron ball too. You can give a try with any of them. So there will be a different kind of oscillation, and depending upon position where you left your oscillating magnet. Suppose we started in the mid position, then the oscillation will be different. We started with the top of one magnet, the oscillation will be different. And instead of 3 magnets, we put 4, 5. Okay. Just play.
Yeah. Okay. So I have another question. I think. So any other question from the audience? If not, then I'll ask one more. Okay, let me ask. So, Pankaj, can you just tell me once again about the anti-periodicity? Can you explain once more?
Come back here. Just look at this three-peak curve. Okay.
Yeah.
Just look at here. And
yes.
So this is the periodic repetition. Okay.
Right.
From here to here. So this may be the T. But look at this position. This is halfway around.
Okay. Sure.
So this point is, suppose is X, then this point should be minus X.
Right.
So this is the anti-periodic. Means it's following the rule X T plus capital T is equals to minus of X T. But suppose you have this kind of periodic signal.
Yes.
So this is also periodic. This part is repeating. However, this is not anti-periodic.
Right.
Because you have minima here, but you don't have minima here. So this is not. So all periodic signal can't be anti-periodic. But all anti-periodic signal must be periodic.
Might be periodic. Yes. Okay. So I have last generic question that one more question before that. Suppose we are going through the pandemic situation, this COVID situation. So I think this a lot of application is there. Also nonlinear dynamics in analysis of this, how the virus is spreading, how their dynamics. These things also, I think, a lot of nonlinear dynamics is involved with there, right?
Yeah. Actually, I recently started working on this. Let me share one important result out of that. But because the data is completely changing every day, it's very difficult to keep up the pace with the college schedule and all those things.
Right.
What I found out that I was doing some kind of analysis nonlinear, and I was calculating one factor, and whenever that factor is beyond 0.3, then there was a peak. So I have to check when we will get the peak in the second phase. But in the first phase, because I have complete data of that, so I analyzed for many countries, and I found out whenever that point is beyond 0.3, then we are seeing a peak in your data. So
what is that factor? What is the name, technical name of that factor?
I was calculating instantaneous frequency.
Okay. I see.
And that 0.3 can be different from you, but it should be some kind of general term, because I analyzed with the various countries' data, and I always found that whenever countries' instantaneous frequency reach the 0.3, that may be depending upon my normalization. You can normalize with something else, then you will have some different factor. But that should be common for every country. So even you can analyze your data with these nonlinear things. Not only with the COVID pandemic, you will find the nonlinear data analysis, and you will find out many applications. Even in
it has lot of applications there. Yeah, everywhere is there. So can you to our students? So I am this. I think this question is towards keeping in mind about the young students. So can you prescribe the institutes, means where means since you are expert, so can you suggest that particular area, the areas or institutes where they can go and do research or do these things, nonlinear dynamics?
See, as I have recently switched from the research to teaching background. So, from the student perspective, even I don't have lots of questions in my mind as a student. So, I first encourage all the students to apply anywhere. It doesn't matter. Don't try to find out the position at particular place. Just apply wherever you have find position. Okay, for the summer project. Right now it's a pandemic, so there is no direct physical visit of the lab, but still some lab work are provided by many people in the theoretical work. So if you want to do the practical, just do in your lab. But in future, when the situation get normalized, never think that you are a BSc student. That's why you will not get the chance, or you are not from the IIT, so you will not apply. Many research institutes asking for the students, and many labs
Yes,
are
yes.
available. So
Yeah.
near, you just apply in your near about in IITs, in Vidyasagar University, or
Yeah,
in
yeah.
Calcutta's like either Kolkata, SINP, they are continuously seeking from the project student. So what I
Yes.
found out that in college students, they have a lack of bit confidence that I can't go somewhere because I'm a PhD student, I'm not from the IIT. So there are, or we have a mind like these are the IITs, so there may be something bigger, not reach of me. It's not like that. Just apply and you will find out that you can easily get the position. Initially I thought like that, but finally I thought out that is very easy. But it's better to keep research in your mind. Like even if you think about the ISR student, they are not different from your background. But whatever they got the exposure about the research. So as I said,
Yes.
do tabletop experiments in your lab. Always be curious about your lab instrument. That's it. Even the tabletop experiment can generate a very significant result. So always be curious about it. When I visited lab, I saw that many students using op-amp but don't know about the op-amp. Using pod, they don't know about the pod. Just be curious and be research friendly. That's it. Apply everywhere.
Yeah.
Wherever you can.
Yes. Also, those people from the maths backgrounds are there. For there are also a lot of scope, I guess, because there is, I mean, this numerical methods and computer programming is also all very much important. Apart from the this experiments, right? Lab experiments, tabletop experiments. So in this subject, both theory and experiment goes together.
Yeah.
So that is a that is
See,
very
it just-
interesting thing.
So important thing about this topic is you don't have to link to particular subject. So that's
Yes.
why you get the scope all the universities. Even
Right,
some
right.
find out that somebody is written just some. Initially, I used to write like from the plasma physics background, but I was doing nonlinear dynamics. I
Yes.
visited Israel, and that people are from the ecology background. They are doing work
Right,
on the
right.
vegetation pattern. But I was there. So
Yes.
from the non-linear dynamics, you can fit everywhere. You just look for the particular person which are from any field but working on the non-linear dynamics
Nonlinear
and just say,
dynamics, yeah.
sir, I want to work in equation. Then you just find out that kind of person. Everywhere is available. Sir, I want to do the experiment. It's available. Sir, I want to do the data analysis. They are also available.
Thank you, Pankaj, for motivating our students. And it is a great talk, actually, a very lucid one. So I hope that everyone. From the I hope there are many questions from the audience as well. But since the timing is running out, so let us
Means if you
conclude
don't-
here. So
If you
yes.
don't have any problem, then we can continue question if you want.
Yeah. From the audience, is there any other question? Please go ahead. So I think for now there is no more question. So okay, but I think later the audience can directly ask our speaker about their questions. Maybe or in future for any guidance is required, I'll request them to directly contact Pankaj. And so now we'll conclude our webinar today. So Himanshu sir is there? Himanshu sir?
Yes.
Sir, please can you just conclude with the vote of thanks?
Today's webinar, the Nonlinear Dynamics and Its Application to Complex System, just completed successfully, and eminent scientist and scholar Mr. Pankaj Kumar sir just delivered his speeches lucid way. I would like to thank him and our college IQAC convener and principal of our college, Dr. Shammu Mahali, and IQAC coordinator, Dr. L.K. Doloi. They encouraged many times that is our department to organize such webinar. So we thanks to them for their encouraging, and we now would like to thank the convener and Dr. Somujana for his intensive work and sincere support from other teacher Ravindranath Ramanik, Sandeep Jana, Nirupam Maiti. And lastly, I would like to thank to the audience who are our colleagues, our ex-student, current student, and our colleague at different college of our university. So, lastly, I thank to our college at last, obviously, for their sincere support, and thanks to all.
Thank you, sir. Thank you very much. So now we'll end this session, the webinar session today, and those who want the e-certificates for this today's state level webinar. So I will send the Google the feedback form to you, and after submission, responding to the feedback form, you will immediately get the e-certificate. So that will be done within a day. So thank you very much. Thank you all for listening to the seminar recently and attending. Thank you. Okay. Now we'll end.